last week talking about the concept of equilibrium. We talked about what equilibrium was and how we could affect it by changing certain conditions like concentration, temperature, and pressure. And so last week we did pretty much all of the qualitative aspects to equilibrium. We talked about what it was by concept and what we could observe about it. This week what we want to do is make that quantitative. We want to actually put numbers to this concept. And so when we do that, we're primarily going to be using what's called the equilibrium constant. And in calculating an equilibrium constant, we'll be able to predict certain things about our system. So let's take a look. Here on this slide is just a general chemical reaction. So we've got two reactants, A and B, reacting to form two products, C and D. Our chemical compounds would be represented here by the capital letters. So we've got the compound A and compound B. And the lowercase italic letters would be where our coefficients would be. This is where numbers would be. This is the A moles of compound A. So if this little a could have been a 2, it'd say that there were 2 moles of compound A. So this is just a very general form for any chemical reaction. And what the equilibrium constant is going to do is tell us the ratio of products to reactants at equilibrium. So the equilibrium constant is represented by KEQ, the constant at equilibrium. Like I said, it's the ratio of product concentrations to reactant concentrations at equilibrium. And the way we write this is as a fraction. We put our products on top, reactants on bottom. Notice a couple things about this. One, everything is in square brackets because remember, putting something in a square bracket means we want the concentration of that substance. So this is specifically saying the concentration of compound C. It's not moles of C, it's not liters of C, it's not grams of C, it's not any other measurement. The square brackets mean it has to be a concentration, a molarity, moles per liter of C. And second, we have raised each to an exponent that's given by its coefficient in the balanced reaction equation. So to write these for any reaction that we could come up with, we'd have our concentration of each product raised to its coefficient. The concentration of compound C raised to the coefficient in front of it. The concentration of compound D raised to the coefficient in front of it. And we've done the same thing for our reactants. We've got the concentration of compound A raised to the coefficient of A. The concentration of compound B raised to the coefficient in front of compound B. We'll do some examples with writing these in just a moment. One important thing to remember though is that we only need to include gas and aqueous phases when we write this expression. And the reason behind that is that, again, we care about concentrations. So gases can have a concentration. Picture a 1 liter container. We can put some number of gas molecules in there, right? Say we put in 1 mole of gas molecules. Great, we've got a concentration of 1 mole per liter. But we know that gas molecules are spread out very far apart from each other, and we can push them closer together. We could add in more gas molecules. So say we add in another mole. Now we've got 2 moles per liter. Our concentration changed. We can compress it. We can concentrate it. And so our concentration matters there. It means something. Same thing for aqueous phases. That means a compound has been dissolved in water or another solvent, and we'd have a concentration, but we could dissolve more. We could change that concentration. The reason we don't care about solids and liquids is because concentration doesn't really mean anything for a solid. It's not really going to change. Think about a block of iron. What's its concentration? Well, I don't know. It's 100% iron. Can you make it more iron? Can you squeeze the iron together and make it more concentrated? Not really. So you can think of it, if you want, you can think the concentration for those is constant. It's not changing. It's always 1. Putting it in this expression wouldn't matter. It wouldn't mean anything. Same thing for liquids. You can't just squeeze water to try and force more water molecules close together. Solids and liquids are pretty much 100% themselves. You can't just force more moles of iron or gold or metals into the same space, right? You can't compress a brick. It's a brick. It's going to stay a brick. It's 100% that brick. We can't make brick concentrate. It just doesn't work. So when we do full examples, we will always have to specify the phase of any of our compounds, because when we go to write the equilibrium equation or expression, we only want to include gas and aqueous phases. Alright, let's look at an example. One other thing to remember is that the value of our equilibrium constant is going to depend on temperature. So, practically speaking, anytime we deal with an equilibrium constant, the temperature is either going to be specified to be an exact value, or it will be specified that it's constant. If we're going to be using an equilibrium constant, we have to have our temperature staying at a constant value. If the temperature is changing, this number is going to change as well. And this example here is just to sort of demonstrate that to you, so that you'll believe this statement. So we've got this equilibrium here between dinitrogen tetroxide and nitrogen dioxide. This gas happens to be colorless. This gas happens to be brown, and we've put the same amount initially in both of these flasks and then let them reach equilibrium. The difference is that this one is in warm water and this one is in cold. So you can clearly see there's a difference here. This one's much darker brown, so it must have more nitrogen dioxide gas. They started with the same amount, they just reached different equilibrium ratios because they were at different temperatures. This gas happens to be the more stable one in warmer temperatures. The whole point of this slide, though, is just to say that we can only use an equilibrium constant for one specific temperature. If we change the temperature, that number is no longer good. And then the reason we care about an equilibrium constant is that its magnitude can tell us whether reactants or products are going to be more favored at equilibrium. It'll tell us which one's going to be more common, more present. So let's think about this on our own first. Let me go back a couple slides. Here is our equilibrium expression. Let's say that this number k is really large, way bigger than 1, huge number. What does that tell us? Which one of these, products or reactants, numerator or denominator, is going to be bigger? Well, for this number to be much bigger than 1, this top number must be much bigger than the bottom number. And this top number is where our products are. So if this number is bigger than 1, it indicates that more products form than reactants. If this number is bigger than 1, then our equation forms a lot of product. If this number is less than 1, same thinking, now our denominator must be the bigger number. If this number is less than 1, the reactant concentration must be greater than the product concentration. And so those rules are summarized here. When k has a large value, such as 3.1 times 10 to the 11th, that's a very big number, right? That would indicate to us that the reaction mixture at equilibrium will have mostly product. This number was equal to products over reactants, so for it to be so large, the product concentration must be much larger. Same thinking, if this is a small value, how about 3.1 times 10 to the negative 11th? This will be a very small number, much less than 1. And that would tell us that the equilibrium mixture is mostly reactant. Now if we get an intermediate value, no really big powers of 10 in either direction, that means we're in the middle. We've got some of both. Some product, some reactant. We've got a fair, significant, decent amount of both compounds still in our mixture. Alright, time for a couple of examples. We're going to use that same equilibrium system that we saw in the flasks earlier. So recall, we've got dinitrogen tetroxide, a colorless gas in equilibrium with nitrogen dioxide, a brown gas. The double-sided arrow indicates that they are at equilibrium, and we have specified both phases here as gas, so both of these are going to have a concentration that matters in our equilibrium constant. Alright, so let's see what our given information is. We have 1 liter of a gas mixture at equilibrium, and we know that it contains 0.0045 moles of dinitrogen tetroxide and 0.030 moles of nitrogen dioxide at a constant temperature. We want to know two things. We want to write the equilibrium expression, so the expression for the equilibrium constant, and we want to actually calculate the value of that equilibrium constant. Alright, so our given information here tells us something very important. We have a number of moles in a given volume. So for each of these, we know their concentration. Concentration is moles per liter. We've got a number of moles in 1 liter, so we've got their concentrations. Again, represented here with the square brackets. We're looking to do two things. We want the expression for the equilibrium constant, and we want its actual numerical value. So we have to start here. Remember, our expression is products over reactants. Let's go back, look at our expression. Here's our product. We're going to have the concentration of NO2 raised to a power of 2, because 2 is our coefficient here, and that'll be in our numerator, divided by our reactant concentration. And there's no coefficient here, there's no number, so it just has an exponent of 1, which doesn't need to be written. So here's our equilibrium expression. And then to get the value for that, this is the ratio of products to reactants at equilibrium. To get an actual number, we just need to plug in those concentrations at equilibrium. Alright, and we already knew those. Those were given to us in our problem. And so we just plug those numbers in here. It's very important to remember that in the equilibrium expression, you can only plug in concentrations present at equilibrium. And that's what the problem gave us. They let the system reach equilibrium and then told us that these were the amounts of moles present in 1 liter. Once we have those numbers, we can just plug this into our calculator and solve. Great news for you about the equilibrium constant. Like I said, it's just a ratio. It's the ratio of products to reactants. All we need is the number. This is 1 time. You don't have to include a unit. You can just drop it. You can leave it out. In fact, that's the standard way to do it. No unit necessary. And then you can evaluate your answer. Make sure you followed all the steps and that it makes sense. We got a value here of 0.2. It's a pretty intermediate value and would indicate to us that the equilibrium mixture contains a significant amount of both gases at equilibrium. Let's do one more. There's a bit more thinking involved in this one, but it's a pretty good problem. So let's talk through these steps. This time we're given 1 mole of hydrogen gas, 1 mole of iodine gas. They're in a sealed 1-liter flask, so we know the volume, and we know the starting moles of each. And they're allowed to react at a constant temperature. At equilibrium, we have 1.56 moles of hydrogen iodide, our product, together with some of the reactant gases that did not react completely. And we would like to calculate the equilibrium constant for this reaction. So the first thing we need is a balanced reaction, which is shown down here. So we've got it balanced, we've got all the phases specified as gases. We'd be able to write an equilibrium expression for this, which we'll get to in just a moment. And let's look at what we were told. Now, at equilibrium, we have 1.56 moles of product and some reactant. So we know how much of this we have at equilibrium. We're not sure, just looking at that statement, how much of these two are present. It just says some. It's very important to note, our equilibrium concentration of these two is not 1 mole per liter. That was our initial concentration, and we can't plug initial concentrations into our K equation because this wants equilibrium concentrations. It wants the ratio at equilibrium. These may have been initially present, but then they react and they change, and once we reach equilibrium, we have a certain amount of this and a certain amount of this. So we're not sure just yet how much of this we have, but we can reason it out. So let's write down the things that we do know. Like I said, we know our equilibrium concentration of product. So we've got a starting point. And we know how much of this we initially started with. To figure out KEQ, we'll have to know how much of this is left at equilibrium. Let me go back for a second. We know how much of this we're producing. We know how much of this we're starting with. We can use stoichiometry information here to figure out how much this has to decrease, how much we have to react and use up to make our product. So here's what that looks like. We are looking for how much reactant was consumed in the reaction. So we don't know that value. We're just writing it as a variable here. Let's make it be X. If we consume X amount of hydrogen gas and X amount of iodine, we know we're creating 1.56 moles of product. Now, the reason these are both X is because, remember, looking at this equation, if we consume some amount of this, we have to consume the same amount of this, right? They're 1 to 1. According to our equation, if we were to react 2 moles of hydrogen, we would also need to react 2 moles of iodine in order to make any product, because equal amounts of these are present in this reaction. So when I made this one X, I also knew that the same amount of iodine had to be used up to make my product. Now, I can solve this expression for X, no problem. X plus X is 2X. I divide both sides by 2 to get a number for X. And this tells me how much of each of these I consumed in my reaction to make my equilibrium amount of product. So from that information, I can figure out how much I have left. So we want to know how much of each of these reactants remains at equilibrium once we've reached equilibrium. And again, we know they're going to be equal because of our balanced chemical reaction. We know we started with 1 mole. We just solved for X and found that we used up 0.78 moles. Therefore, we know that we have 0.22 moles of each left over at equilibrium. This amount was used up to make our product. This is what we started with. The difference is what is left over. All right. Now we can write our equilibrium expression for K. Again, based off of our chemical reaction equation, we've got products over reactants. Our product had a 2 in front of it for its coefficient, so it is raised to the second power. Our two reactants did not, so we've just got the concentration of each of these. And now finally we have all the information we need to plug in numbers here. We know our concentration of product at equilibrium, and we know our concentration of each reactant at equilibrium. Again, it's absolutely necessary to plug in a number into this equation. It has to be an equilibrium number. It has to be there at equilibrium at the same time as everything else. So we put these numbers into our calculator and solve. We get a value of 5 times 10, 50. Again, a fairly intermediate value would indicate to us that both reactant and product is present at equilibrium. Alright, now that is the way your textbook takes you through those problems. That's what you'll find if you go read through your textbook. I think there's a slightly easier way to set these up, so I'm going to show you an alternate set of steps to solve this type of problem. If you liked that first one, that's fine. You can use that one, no problem. I find this a bit easier. This strategy is called making an ICE table. ICE stands for initial, change, and equilibrium. So when we make this table, we've got a box. We've got a place to put all of our relevant numbers. And so up here I've written out that chemical reaction again, and I filled in some of our information. So the first step in the ICE table is writing down what you have initially, what you start with in your reaction container. And remember, we started with 1 mole of each reactant in a 1 liter container. So we start with 1 mole per liter of these two, and we start with 0 product. They have to react to make the product. So this is our initial concentration of each of these 3. Now we want to fill in how much each of these is going to change by. In general, I'll make these all in terms of x first, and I'll fill in numbers later. So I don't know how much they're going to change by, not yet. I would need more data for that. So I'll just say, hey, I know these two are going to react, so my concentration of them is probably decreasing. It's probably going down if they're used up to make a product. And let's just say this one goes down by some amount x. I'll do everything else in terms of this one. If my hydrogen gas is decreasing by some amount x, I'm using up some amount of it, I must use up the same concentration of iodine gas, right, based on these numbers. So I've got minus x for both of these. That's how much it's changing by. And now I need to know how much product I will make if I react x amount of each of these. And if I react some amount of each of these, I produce twice that amount of product. If I react 1 of each, I produce 2. If I react 2 of each, I would produce 4. If I react x of each, I produce 2x. Okay? So I have filled in sort of an expression here to determine how much each compound is changing by. And to get a box for equilibrium, I'm just combining these two boxes. At equilibrium, let me go through this. At equilibrium, I would have 1 minus x of hydrogen, 1 minus x of iodine, and 2 plus 2x of my product, hydrogen iodide gas. Now, for this problem, I happen to know how much the product changes by. I happen to know how much of it I have at equilibrium. I was told At equilibrium, I have 1.56. Well, now I know what x is. I have a way to solve for x. I know that this change box has to be equal to 1.56 because 0 plus this box has to equal 1.56. So I can solve for x. 2x has to give me 1.56. So I know that x was equal to 0.78, and I've put that into these boxes. Again, I know this box has to be 1.56 because I know how much is present at equilibrium. These boxes change by half of that, and so I've plugged those numbers in here. Now I know what I'm going to get at equilibrium. Again, combining these boxes, 1 minus 0.78 gives me my equilibrium amounts of these two. And now it is always, you have to get the full equilibrium row in the table filled out, because these numbers, the ones in the equilibrium boxes, are what have to be plugged in to your expression for K, the equilibrium constant. And now, just as before, I've got this data, it's in my ICE table, I plug these numbers in where they need to be in my expression for K, and I solve and get the same answer. I think this strategy is a little easier just because it gives you a place to put everything. It's a bit easier to organize your thoughts because you've got a table and you just need to fill it out. If you're given initial concentrations, great, they go in their box. If you're given equilibrium, great, they go in a box. If you're given a change, great, they go in a box. It helps keep the given information straight. That way you don't read through a problem too quickly and accidentally use an initial concentration in your equilibrium expression. It's much easier to organize and just know that this bottom row of numbers is what you have to plug in. Alright, one more example. This time we've got bromine chloride gas decomposing to form bromine and chlorine. So we start with this balanced equation. We've specified that all phases here are gases. And now for our given information. At a certain temperature, the equilibrium constant for the reaction is 11.1. So this time we're given K. We've got a certain temperature remaining constant, and we know K. We know that a sample of pure bromine chloride is placed in a 1 liter container and allowed to decompose. At equilibrium, the reaction mixture contains 4 moles of chloride, and we want to know the equilibrium concentrations of bromine and bromine chloride. So that's a lot of given information. We need to organize that first. So let's see what we were told. We were given our equilibrium concentration of chloride gas as 4 moles per liter. And we were given our value for K, the equilibrium constant, 11.1. And we know that temperature is constant. We're looking for two things for this problem. We're looking for the concentration of bromine, one of our products at equilibrium, and the concentration of bromine chloride, one of our only reactant at equilibrium. So this was fairly different from the last problem. This time, we don't know our initial concentration of reactant. We were just told a sample. Some of it is put into a 1 liter container, and it decomposes. Instead, we know the concentration of one of our products and the equilibrium constant. So what we're going to do is we're going to calculate the concentration of bromine at equilibrium. So this comes from, let me go back, this comes from, again, our balanced equation. This is something we had to figure out just based on stoichiometry. We are told that we get 4 moles of chlorine at equilibrium. At equilibrium, we've got 4 moles of this product. Well, we can't create chlorine without also creating bromine, right? They're being produced because this is breaking apart. If enough broke up to make 4 moles of chlorine, we also have to have that other half, the 4 moles of bromine, floating around somewhere. And so we know how much of this one we have as well. We know these have to be equal because they have equal coefficients, equal stoichiometry. So that's our first step. After we know how much bromine we have, knowing that it's the same as the chlorine at equilibrium, we can write our equilibrium expression for the reaction. So again, we've got our products over our reactants, any coefficients acting as exponents. And we know all but one of these numbers. We know the value for K. We know the concentration of both of our reactants because we know they're equal. And so we're able to solve for the concentration of our reactant. So let me go back. To get from here to here, we multiplied both sides by the concentration of bromine chloride squared to move it over here, move it out of the bottom of the fraction. We multiplied it over here. And then we're going to divide both sides by KEQ to get the bromine chloride by itself. So we've got the concentration of our reactants squared equals the concentration of our products over K. And we've got all these numbers, so we can plug them in and solve here. We've got the concentration of bromine chloride squared equals 1.44 moles squared per liter squared. And then to get a final value, we need to take the square root of both sides to get rid of that squared term. And so we've got a final answer, the concentration of our reactant at equilibrium is 1.2 moles per liter. And it should make sense that we've got a concentration fairly similar to the concentration of the products because our value for K was 11. It was an intermediate value, and we got a close enough concentration to show that both reactants and products were present at equilibrium. Last one, we've got hydrochloric acid, or hydrogen chloride, is formed when hydrogen and chlorine gas react at high temperatures. At equilibrium, we know the concentration of hydrogen chloride is given, and we know the concentrations of hydrogen and chlorine are equal and equal to 1.6 times 10 to the negative third. We want the value of the equilibrium constant. No problem. We can write an expression for the equilibrium constant based on our reaction. Products over reactants. Our product has a coefficient of 2, so we'll have the concentration of hydrogen chloride squared over the concentration of each reactant, and we know their equilibrium concentrations already. So we're just plugging those numbers in to solve. Alright, so hopefully those examples made sense and are helpful to you on your homework. The hardest ones are definitely the ones that require an ice table, but if you give it a bit of practice, it's a very helpful tool for solving that kind of problem.